Hello, everyone, and welcome to Lesson 5 of Physics Summer Courses. This officially marks the halfway point. Congratulations to all of you out there who've been watching and keeping along. Today we're going to be continuing our conversation on forces. This is Forces Part 2, and basically what we're just going to add is two things we have not really talked about yet. Number one is multiple objects, like two or more objects in one problem. And the second is friction, which is one of the biggest topics in all of physics, especially with forces. So with that, let's get started with a quick review of what we did last time. Basically, the three-step process, well, 3.5-step process for solving force problems. Number one, draw a free body diagram. Remember, this is a picture with all the forces, whether it's normal force or gravity force or a pulling force or a pushing force or tension force or whatever. Draw all your forces on the free body diagram. Step 1.5, I like to call it. That's if you have any vectors at an angle. Of course, those forces need to be split up in the x and y component, and the way you do that is by drawing a right triangle. Step 2, Newton's second law. That's the one that says F net equals ma, and you can do that for either the x direction or the y direction. And then finally, step 3 is solve. Now basically what we're doing today is just a continuation of this, so let's talk about what's different when we have multiple objects in one problem. The first thing that's going to be different is you need to draw a free body diagram for each object. So for instance, if you have three objects, you're going to need three free body diagrams. And that's pretty straightforward, so it's not going to be too bad actually. I'm already out of room basically, so I'll go on the next page. Step 2, or at least the second thing that's different, is that you're going to use F net equals ma for the system, which sounds very familiar to the end of last week when we talked about the Pauli problem when we looked at the system. Yeah, it's the same idea. The system is basically all objects in the problem. You group them all into one big happy object. And then what you're going to do after that is you're going to be solving for acceleration. That's the goal. The reason why we group it up together is so you can find the acceleration. And then the third thing you're going to do is... Go ahead.
Oh, can I ask a question?
Go ahead.
So, I'm a bit confused. So, what would F net represent again?
Yes.
Clarify.
Yes, no, that's a good question, because I should not assume that you guys have been doing it for 8 years like I have. F net is, for instance, F net x, is all the forces to the right minus the forces to the left. And F net y is equal to all the forces going up minus the forces going down.
Is it always like this, or can it vary in certain situations?
It's basically this. Yeah, it's basically this.
Sorry, I don't understand.
Sorry about that.
Yeah, I have a Google as well. So it's funny because whenever I say, oh, cool, like I did just now, it's probably going to pick it up and think I'm talking to it. So I will not say, oh, cool, like I just did. And then the third step is we are then going to use F net equals ma for individual objects. Depending on what I want to solve for, maybe I'm looking at one object or another. But basically, first you look at the system, all of them together, then one object at a time. Any questions with that?
That's good, thank you.
Okay, excellent. So then now we are going to go into our first practice problem. Number 1, a 100 Newton force is being applied to mass A and mass B. As you can see here, they are touching each other. And what I would like to know, what is the force of A on B? So the first thing I'm going to do is I'm going to draw all the forces acting on each box. Now, in my opinion, I think it's a little cluttered. If I want to draw them on here, it's going to be too close for comfort, I guess you could say. So let's draw the boxes separately like this with some breathing room in between. So now there's plenty of room to write it. Also, you'll probably have to write small, so be careful. So first, I want to say that there is a normal force on A, Fn, and there is a gravity force on A, mg. To the right, you can see that 100 Newton force. I'm going to draw the 100 Newton force going that way. In other words, technically I can draw it going this way into the box, but in general, a good rule of thumb, always have your force arrows going out of the box. That means going to the right like this. And then, are there any other forces? There is one more, but I'm not going to say what it is yet. Now on to box B. Box B, again, same thing, normal force going up, gravity going down. And here's the thing about box B. If I were to write this 100 newtons to the right, that would be incorrect. I'm going to erase that. And the reason why it's wrong is because that 100 Newton force is not touching box B. It's touching box A. So it can't go on the free body diagram for box B. So what does point to the right on box B? And the answer is the force of A on B, which I can call that. And that's also the answer to my question, so that's what I'm solving for. Now, one thing Newton's third law tells us from last week. Newton's third law says for every force there is an equal and opposite reaction force. What that means is that there is also force B on A pushing in the opposite direction. If I were to draw it up here, it would look like this. Force A on B going to the right, force B on A going to the left, just like that. And because they are Newton's third law forces, I know FA on B must equal and cancel out FB on A. And again, that's because of Newton's third law, if we remember from last week. So now we're done the first step, and what I want to do now is I want to write the free body diagram, the Newton's second law equation, F net equals ma, for both boxes combined. Now another thing I have to decide is, do I want to do F net x or F net y? Well, what am I solving for? I'm solving for force A on B, right? So in other words, I'm choosing F net x, and I'm choosing it for the system. So I'm going to mark that on my paper as such. Always better to have too much writing than not enough with your notation. And then I'm going to say that equals the forces to the right. What forces point to the right? I have two of them. I have force A on B, and I have the 100 Newton force as well, so plus 100. And then minus the forces pointing to the left. There's only one, it's FB on A, so minus FB on A, just like that. And as always, I set that equal to the mass times acceleration. And whenever I write this, I should ask myself, do I know the acceleration? And the answer is no, I do not. That's probably what I'm going to be solving for first. It also gets better because even though I don't know FA on B and I don't know FB on A, since they're equal to each other, they cancel each other out. So in other words, what I have here now, I've got 100, that what's left equals ma. That mass is the total mass, meaning 100 equals mass A, which we said was, 15 kilograms, plus mass B, which is 10 kilograms, times A. So that means 100 equals 25 times A. Just divide both sides by 25. It looks like you'll get A equals 4 meters per second squared. And remember, that's not just true for the one box. That's true for all the boxes. All the boxes are accelerating 4 meters per second squared. So we're done that. We looked at the system. Now what should we do? Well, now we're going to look at one of the boxes individually. It doesn't matter which one you choose. You can choose box A or box B. Since I think box B is going to be easier because there's less forces acting on it, I'm just going to focus on box B. Now, you don't have to redraw it, honestly, like I am because it's on a different sheet of paper, but I'm just drawing the exact same thing we drew earlier. And now what I'm going to say is if I do Newton's second law, which I will say F net, comma x, comma b, because this is just box B now, that's equal to all the forces to the right, FA on B, minus the forces to the left. There are none. You can write minus 0, although you technically don't even have to do that. And then you say equals ma. Now this mass is no longer both masses together. Now it's just the mass of block B. So FA on B equals, mass B is 10 times the acceleration, which is 4. It looks like FA on B is going to be 40 newtons. And there's my answer. Now, by the way, I will say, we could have done box A, and let me just show you what happens there. You don't have to write this down if you don't want to. I just want to show you what happens for box A if you do the same thing, because you should get the same answer. So we said 100 newtons to the right, force B on A to the left, which is technically the same thing. So that means that F net, comma, X, comma, A for box A, that's sloppy, let me try that again, box A, better, equals 100 minus FB on A, and that equals mass A times the acceleration. So it's going to be 100 minus FB on A equals mass A is 15 times the acceleration is still 4. Looks like 100 minus FB on A equals 15 times 4 is 60. So then I'm going to add F of B on A on both sides. So 100 equals 60 plus FB on A. And then we just subtract 60. It looks like 40 newtons, again, is going to be the same force. And like I said, these two forces should be equal to each other, FB on A and FA on B. So that's perfect. Any questions on that first one? Okay, great. Now
I'm
into...
confused.
let's hear it.
Could you go over how the forces would cancel out again?
Yes, absolutely.
I think I'm a bit confused with that last part. Because wouldn't the force on box A be greater than the force on box B because it weighs more?
No, I see what you're saying.
Right.
And that's a common misconception in physics. It's one of the most classic misconceptions. And that is to say that like the bigger box has more force than the littler box. And that is actually not true. And why is that not true? Because of Newton's third law. And what does Newton's third law says? It says that every force, like for instance, Fa on B. Let me finish writing this. This is Newton's third law, is what says this. You got a force Fa on B. That has an equal and opposite force Fb on A. And I don't just get to say equal and opposite because I feel like it. It's equal and it's opposite. Opposite directions, and they have to be equal. It's the same reason why, and this is always my favorite example, if I push you down the stairs with 30 newtons of force, technically you pushed me with 30 newtons of force, and that's why I'm going to call the teacher on you and get you in trouble. Does that make sense?
Yep, thank you.
No problem. And by the way, I would only push you down the stairs in a hypothetical example, never in real life. I'd get sued. So, anyways, number 2. We have 3 boxes, and I would like to know what is the tension in each rope, T1 and T2, in terms of M and F, mass and force. So this is the first time we've seen this summer, but I'm going to tell you it's a very common kind of question they love to ask in physics. And that is, they're going to give you no numbers. They're just going to tell you the mass is M and the force is F. And what you do when there's no numbers is you literally don't plug in any numbers, okay? I know that sounds confusing. If it makes you feel better, you can plug in any numbers you want. It's probably going to hurt you more than help you. But here's what I'm saying. First, if I want to solve this, I got to draw the free body diagram for each of these. So for this one, I'm just going to draw directly on the picture. It doesn't matter. These are spread apart. They're not touching directly. So for the left box, I have 3 forces. Normal force going up, mg going down, and a tension force we call T1 pointing to the right, just like that. Now for the middle box, same idea. Fn pointing up, mg pointing down. But this one has 2 forces acting on it. We got T1 pointing to the left and T2, tension 2, pointing to the right. And then, of course, for the third one, we got, again, a normal force, again, mg going down, T2 going to the left, and a force F, which is already here. F is pointing to the right. And by the way, what I want to say is that the tension in the rope, see how it shows up twice? Once for each box, like T1, T2 shows up twice. That, again, is because of Newton's third law. Newton's third law shows up all the time when you have multiple boxes. When you only have one box, like just about every example we looked at last week, we didn't even have Newton's third law. You really only see Newton's third law when you have multiple boxes, okay? So, now I'm going to say to look at the system, because that's what you should do. You should always look at the system first. And since tension points in the x direction, I think it's going to make the most sense to do F net x for the system. So let's count the forces from right to left. First, you got force F right here. That's positive because it points to the right. Then it looks like that T2 in green points to the left, so minus T2. Then T2 in red points to the right, so it looks like plus T2. That will cancel. I'll cancel it in the next step. The next force is that red T1 pointing to the left, so minus T1. Then finally, the last force, blue T1, which points to the right, so plus T1. And after I'm done that, I set it equal to mass times acceleration, and I need to remember that that mass is the total mass for all three boxes. So you're going to love this, because look how much stuff cancels. T2 cancels and T1 cancels. All I've got is F, which is not a number, it's just the letter F from right here where my cursor is, equals mass, well there's three masses, right? So I'm going to write mass plus mass plus mass. If I had numbers, like let's say they were each 10, it would be 30, because 10 plus 10 plus 10 is 30. So in other words, what is the mass if I have three masses like this added together? Well, m plus m as a variable is 3m. And I know it's a variable, and I don't care, because it clearly says in the problem I want my answer in terms of mass m and force F. And then, of course, still times the acceleration, and now I need to solve for the acceleration. Now, this part is probably going to confuse some of you out there because you're so not used to it, but I'm telling you, everything I'm doing is completely okay and correct. I need to solve for acceleration. Here, how do I do that? Divide both sides by 3m. This is going to look weird, but the acceleration is F over 3m. Don't circle that because it's not a final answer, but this is important. We got the acceleration. And if you want, you can plug in any number you want for F. Like you can say F is 100 newtons, and you can say mass is 10 if you want. So 100 divided by 3 times 10, you'd get 100 over 30 as the acceleration. That's all the variables mean. You can plug in any number you want. It doesn't matter. I'm not going to plug in numbers because the problem doesn't want me to. It wants me to keep it as F and M. Hopefully that's not confusing. If it is confusing, just let me know, and I'll try and explain it better next time. So, we're done with this. We got the acceleration. Now if we want to find T1 and or T2, we got to look at one box at a time. Which box would we like to look at first? Audience members, any suggestions?
Oh, I think the first box, the T1.
The left one? Okay, the blue one? Yeah, I would agree. I think that's the easiest one. So, we just have mass M with T1 to the right, normal force going up, and gravity going down. You'll notice for the last two problems now, I don't even care about normal force and mg, only because all my forces I care about are in the x direction. In the next problem, that will not be true, but that's okay. So, here's what I'm going to say. F net left, comma, x, so left box in the x direction, equals T1, and then that's it for the forces. It's just positive T1. And then you set that equal to mass times acceleration. Once again, the mass is m, like that's it. And then the acceleration, we just said it. The acceleration is F over 3m. So maybe some of you don't see this, but I'm going to tell you what I would do is I would say T1 equals mass times F, both in the numerator. It's m times F divided by 3m, and it looks like the masses do cancel. As a matter of fact, we technically could have canceled them in this step because m is in the numerator and the other m is in the denominator. So it looks like our final answer for T1 is F over 3. And if you don't like that, you can say T1 equals 1/3 F. It's the exact same thing. And that is the final answer. And again, it's in terms of M and F. Well, really just F. Yes, go ahead.
So my question is, I noticed that the amount of boxes corresponds to the number in the equation. Is that random, or is it like a pattern? Like if you had 4 boxes, would it be 4?
That's a good question. The reason why it was F over 3 is yes, because there were 3 boxes, and because they were identical. However, one thing I do want to tell you is that you should not just go by that to answer the question. You should do this every time. And as you're going to see for T2, T2 is not going to be the same as T1. Let's find T2 now. So T2, we can either look at the middle box or the right box. Which would we like to look at, the red or the green? Any suggestions?
Should look at the red box now.
We will look at the red. So for the red, again, normal force, which I probably don't care about. Gravity, which I probably don't care about. To the right, I have T2, and to the left, I have T1. Okay, so now my F-net equation is going to be F-net, comma, right, not right, middle, sorry. Middle, comma, x. That's going to be all the forces to the right, T2, minus the forces to the left, T1. And then I set that equal to the mass. This is just the middle block, so just mass, times acceleration. So T2 is what we're solving for right now. T1, we actually just found it. Remember, T1 was F over 3? And then we're going to set that equal to mass, which is just mass m, times acceleration, which was, remember, F over 3m. And once again, these masses will cancel, just like that. So now it looks like T2, well, I should add F over 3 to both sides to get rid of it. So T2 equals F over 3 plus all that's left on the right side is F over 3. Okay, so we get this. And since they have the same denominator, you can add them. And what that's going to look like is F plus F over 3, which, if you prefer, you can write it like 2F over 3, and that probably looks better. And there we go. T2 is 2F, or 2/3 F, if you want to think of it like that. And again, it's very similar to T1. It's the same kind of logic. But again, I highly recommend solving it this way and not memorizing this 1/3 and 2/3 rule. Any questions? Yes. You can just call out. You don't have to do that.
Oh, so my question is this also a pattern as well with the 2? Like, if you looked at, like, a hypothetical fourth box, would it be 4F over 3?
You mean 3F over 4? Yeah. If all the masses are equal, then it'd be F over 4, then 2F over 4, then 3F over 4, and then that's it.
Okay, thank you.
Yep, no problem. So, that's it for that one. Okay, great. Now we're on to friction. Okay, so friction, there's two kinds of friction, and there is static friction and kinetic friction. First, for static friction, this is the friction when something's not moving. Think about when you try and push something really heavy, like a couch, and it's like not moving. You know what I mean? That's static friction. Now, of course, if you push hard enough and you get it to start moving, well then yeah, that's the other kind, kinetic friction. So kinetic friction, that's moving. So it's the first difference between those two. The next thing I'm going to say is the equations. The equations are also different. I probably should start with kinetic, but we're going to start with static, which is harder. So static friction has a weird equation. It's the only equation in physics that has a less than or equal to sign. Very confusing. Now, let me explain what this is. This right there is the static friction force. Static friction force. This right there, that fella, is called the coefficient of static friction. And I'll explain that in the next part, because literally that's what this whole second half of the page is about, the coefficient of friction. And by the way, that is Greek letter mu, pronounced mu, like that. That's Greek letter mu. And then finally, our good friend, the normal force. Finally, a familiar face. Okay. Next, we have kinetic friction. Kinetic friction will be moving. It has an equation. This one's more friendly. This equation is just an equal to sign. Fk equals mu k times the normal force. So in other words, it's basically the same equation, but now I have to explain the less than or equal to sign, and does that matter? And the answer is yes, it does matter. So basically, let's say I push a wall. Let me just give an example. Maybe not a wall. Let's say a box, okay? Here's a box, okay? And let's say I push on it with 10 newtons. This is me pushing on it 10 newtons. And it's not moving. This is not moving. Okay? What is the friction force? Well, the friction force has to cancel out my force, so I'm going to say 10 newtons going the opposite way. Okay? So that makes sense. Now let me do something else. Let's say now I push with 20 newtons, and it's still not moving. Now what's the static friction force? Well, now the static friction force is 20. In other words, it always will match whatever my pushing force is, until I finally get it to start moving. Once it starts moving, and this is weird, once it starts moving, okay, and I push with, let's say, 30 newtons of force now, and 30 newtons was enough to get it moving, and it's going that way to the right, okay? The friction force stays constant. Let's just say, let's make up a number, let's say the friction force is 25 newtons. So in this tug-of-war game, who's bigger? Obviously my 30 newton pushing force. That's why we're moving. And the funny thing about friction, kinetic friction, now we're moving, it's kinetic friction. The funny thing about kinetic friction is, let's say I double it to now 60 newtons of force pushing, the kinetic friction force stays the same. Why does it stay the same? Because here's why. The equation for kinetic friction is this equation right here, mu k times the normal force. And basically when I push harder, I'm not changing this number, because this number is a constant, it's not going to change. I'll explain what it is in a minute. And the normal force doesn't change. Why not? Because normal force is countering the force of gravity, mg, not my pushing force. So for that reason, hopefully this makes sense, kinetic friction stays the same, but static friction is always going to match it. It's always going to match it. Now, what's even worse about this equation, Fs less than or equal to mu s times the normal force, if I ask for the static friction force, you are not allowed to use this equation unless you are talking about the max static friction force. So let's introduce a new topic now. Fs max, the max static friction force. This is basically when you start moving. When you start moving. This is when we use this equation. And the equation is equals mu s times the normal force. That's the only time you can set it equal to. Otherwise, you cannot use this equation. Now, the good news is 99% of the time, if you see a physics problem talking about static friction, they're talking about the point where you start moving. They're going to use words like the minimum distance you need to stop, or they're going to use words like you push just hard enough to get the object to start moving. They're going to see it in the language that they use in the question, that they want you to use max static friction force. And I know I'm talking too much, honestly, right now. It's going to make more sense when we get to the actual practice problems, I promise. But now I do want to talk about coefficient of friction because I still haven't explained that yet. So here's what you need to know. Coefficient of friction has to do with how rough the surface is between you and the object you're pushing and the floor. So in general, if you have a higher mu, a higher coefficient of friction, that means it's a rougher surface. Think of trying to push a box across sandpaper that has a high coefficient of friction versus pushing something across ice, which is a very low coefficient of friction. And basically a rougher surface, that just means there's going to be more friction. Okay, so now this chart on the right, I want to make a little chart showing how hard you push versus the friction you will experience. This is very similar to the example I was just showing a minute ago with pushing a box harder and harder and harder. Basically, the harder you push at first, the harder you push, friction increases just like this. This is the matching your force that I was talking about earlier. Then you get to some point right here where it can't take it anymore. This is the Fs max. It can't take it anymore. You're about to start moving. And when you do start moving, it doesn't level off. It actually dips, and then it levels off like that. And no matter how hard you push, it will always be this. So just to be clear, this is the static region, and this is the kinetic region. I spelled kinetic wrong. And remember, kinetic means moving, static means not moving. The other thing I want to say is that you'll notice, why is there that dip right there? That's because in general, and maybe you've actually experienced this in real life, it is harder to get an object to start moving than it is to keep it moving. In other words, let's talk about that heavy couch example again. if you want the couch to move as easily as possible, you got to get it to start moving, and then it's going to be easier. If you push it a little bit and then stop and then push again and stop, that's actually going to be much harder for you because you have to overcome static friction, which is more force. Kinetic friction is always less. And the reason for that is because μs, the coefficient of static friction, will always be greater than the coefficient of kinetic friction. So for instance, the coefficient of static friction can be a number like 0.5 and kinetic friction can be a number like 0.3. Usually, the coefficients are between 0 and 1. So like 0 less than mu less than 1. This is the normal values you can expect to see. It's almost always a decimal, like 0.45, 0.98. It's almost always a decimal. Okay, so that's enough of me talking about friction. The good news is the actual equations that we're going to do, it's very similar to what we have been doing. It's actually not that bad. But do we have any questions before we get to those? Okay, excellent. We're on to number 3. Number 3. A 3 kilogram box is pulled across a hardwood floor with a force of 15 newtons. The box is accelerating at a rate of 2 meters per second squared. What is the coefficient of kinetic friction between the box and the floor? So this is very similar to any other kind of force problem I would do otherwise. In other words, first thing I'm doing is drawing a free body diagram. I've got normal force Fn going up. I've got a gravity force mg going down. I have my 15 newtons pushing to the right, and then to the left, I have my friction force. Now, is this static friction or kinetic friction? Can someone tell me?
It would be kinetic friction.
You are correct, because we're moving. We know that because it's accelerating to the right at 2 meters per second squared. So that means I'm going to use my kinetic friction equation, which we remember it's Fk equals mu k times the normal force. So now I'm going to do F net x. Why F net x? Because I'm solving for friction basically, and that's in the x direction. So that's all the forces to the right, which is 15, minus the forces to the left, Fk, and that equals my mass times my acceleration. Now the good news is I know my acceleration and I know my mass. So that means 15 minus Fk equals mass 3 times acceleration 2. That means we get 15 minus Fk equals 6. And just solving for Fk, I would add Fk to both sides and subtract 6. 15 minus 6 equals Fk. And 15 minus 6 is 9. So Fk equals 9 newtons. Now I do want to say that's not what we're solving for. This is a great first step, but this is not what I'm solving for. I want to solve for the coefficient of kinetic friction. That's that mu k from the equation. So here's what I'm going to say now. I'm going to say Fk equals mu k times the normal force. I know Fk, we just said it, it's 9. But now how am I going to find the normal force? Well, here's what we're going to do for normal force. If you remember from last week, I told you the equation for the normal force. And that, of course, is there is no equation. So then how am I going to find normal force? What we did last week, whether you remember or not, is you did F net in the y direction. Let me explain. If we go back to our diagram, in the y direction you only have two forces, normal force going up and gravity going down. And since we know the box is not floating up in the air and it's not tunneling into the ground, it's going flat across. In other words, those two forces must equal each other out. They're not Newton's third law forces exactly, they're not, but they are equal to each other because it's stationary on flat ground. So you can write Fn equals mg, or if you want me to show you why it is exactly, I can show you with the F net y equation right here. So F net y equals all the forces going up, normal force, minus the forces going down, mg, equals mass times acceleration, and that acceleration is 2. Just kidding, it's actually 0. Why is it 0? Because the x acceleration was 2. The y acceleration, because this is F net y after all, that's 0. It's not going up or down. So that means add mg to both sides, and you'll get Fn equals mg, like I said it would. Now the mass we do know. The mass is 3 kilograms, and g is a constant. We know it's 9.8. So that's going to be a normal force equal to 29.4 newtons. And then once we have the normal force, well, now I'm just going to plug it back into my kinetic friction equation. So that means right here, 29.4. And then to solve for mu k is going to equal 9 divided by 29.4, which comes out to a final answer. My handwriting's really sloppy today. But the final answer is going to be 0.306, which is a very normal answer for the normal force. I'm sorry, coefficient of friction. Oh, and by the way, what are the units for coefficient of friction? I forgot to mention that. The answer is there are no units for coefficient of friction. And there's a reason why. Basically, it's newtons over newtons, and the newtons cancel out. But you can just remember no units. Oh, and one more thing I forgot to mention, and this is probably the most important thing, so it's a shame I forgot this. This is back to our notes on friction. This is at the very top right here next to friction. I want to tell you that friction always opposes motion. Friction always opposes motion. So if the object wants to go to the right, friction points to the left, and vice versa. Try and remember that for problem 5, because problem 5 is really hard with that fact. But hopefully you'll get it. And with that, we move on to problem 4. Problem 4. A traveler is comfortably pulling their luggage at a constant speed of 3 meters per second while exerting 150 newtons of force. If the force of friction between the luggage and the floor is 75 newtons, what is the angle at which the traveler is pulling the luggage? So again, same idea. With friction, it's basically the same thing we've been doing, just with one additional step. In other words, my first step is still a free body diagram. I've got a normal force pointing up. I got a force of gravity pointing down. I've already got the 150 pointing at the angle. I'll split that up into x and y components in the next step. And now what I'm adding a force of friction here. This is moving, so it's kinetic friction. And I was so nice, I gave you the kinetic friction. It was 75 newtons. I don't even need the equation this time. But I still need to break that 150 into x and y components. So let's draw a right triangle, like we always should. This is some unknown angle theta. We're solving for theta. 150 is always going to be the hypotenuse, and we're solving for Fy and Fx. So for Fx, that's going to be the cosine, because cosine's touching, it's adjacent. And you can say cosine theta equals adjacent over hypotenuse, and then you can multiply both sides by 150. Fx is going to be 150 times the cosine theta. And then if you do the exact same thing for Fy, I'll just do a shortcut. I'll tell you Fy is going to be the exact same thing except times sine theta. And you can derive that if you want, but you're going to get here anyway. So next thing, we just did step 1 for e-body diagram. We broke the components as well. So now we're on to step 2. And step 2 is saying the sum of forces equation. And since we're talking about, well, probably the x direction because of friction, I think it'd be a good idea to start with the x. And by the way, if you never know where to start, x is always a good idea. It's usually x. So F net x is all the forces to the right. The only force to the right is the x component of the pulling force, Fx. So I can write Fx here, and then minus Fk, which we know is 75, and that equals mass times acceleration. Now, the thing is, we don't know this acceleration. Are we solving for it? Actually, we're not. And the reason why we can't is because Fx is 150 cosine theta minus 75 equals mass, which is... we don't even know the mass. Oh, man, that's a shame. So we don't know the mass, and we don't know the acceleration, and we don't know theta. That's 3 variables we don't know. And the funny thing is, with just one simple fact, I can eliminate 2 of these variables. What is that one simple fact? See how it says it's a constant speed of 3 meters per second? What does a constant speed mean? I'm not sure if I mentioned this before. I think I did last week for Newton's first law.
No acceleration.
Yes, you're right. Constant speed.
No acceleration.
You're correct. Thank you. Constant speed means the acceleration is 0, and because of that, I can just cross that out. It equals 0. So it looks like 150 cosine theta minus 75 equals 0. And now I can solve. So add 75 to both sides. Then divide both sides by 150. 75 divided by 150, that's just going to be 1/2. And then you take the arc cosine of 1/2, which means we get a final answer. If your calculator is in degrees, you'll get 60 degrees, and that must be the angle that they're pulling at. Any questions for number 4? Hopefully that wasn't as bad. Number 5 is the worst problem ever. Well, maybe not ever, but it's definitely the hardest one of today. A truck carrying a crate of apples is traveling at 16 meters per second when it starts to slow down to a stop sign. The coefficient of static friction, notice static friction, between the truck and the crate of apples is 0.5. What is the minimum stopping distance the truck can have so that the crate of apples doesn't slip? I'm going to draw a picture of this. So we got a truck here, okay? Here's the wheels. Big truck. And on the back, we have a crate of apples, which, as we all know, crates of apples are always labeled apples, or else it'd be confusing. Sometimes they have a picture of an apple, but I can't draw a picture of an apple, so this one says apples on the side. Anyways, this truck is heading at 16 meters per second. We know the coefficient of friction between the truck and the crate of apples. So we're not talking about the road. I know this is, the truck's on the road, obviously. But the 0.5 is specifically between the apples and the truck. And here's why that's important. This is an object on top of another object. Whenever you have an object on top of another object, like for instance, the apples is on a truck and the truck is on the road. Whenever you have an object on top of another object, always look at top object. In other words, the crate of apples. Yes, technically there are multiple objects in this problem. Like for instance, the truck is obviously an object, but we don't know the mass of that truck. We don't know the coefficient of friction with its tires. It would be a bad idea to include the truck in this problem. We're just going to deal with the apples. Okay? So for that reason, when I draw my free body diagram, I'm just going to worry about the apples, which means I have normal force Fn going up, got gravity mg going down, and I do have, at least one more force. Basically, here's my thought. Is there any force touching the apples that's propelling it forward? Like obviously, what's moving the truck forward? It's like the gas pedal, the engine, whatever you want to call it. But all that stuff is connected to the truck, not the apples. Is there any force touching the apples? No, except for friction. So there's only one force I'm missing. It's friction. And the question is, which way does friction point? This is static friction. Will static friction point to the right or the left? This is the hardest part of literally the hardest part of today is answering this question right now. Will static friction point to the left or the right? Remember, the truck is moving 16 meters per second to the right, and it's slowing down. So I want you to think about that. I'm going to give you 30 seconds, including you watching the recording. Maybe you just pause the video, and then you can tell me what you think.
Oh, I still think that it's moving towards the left.
And
like
why?
The opposite direction of.
Why do you say the left?
Because even though it's slowing down, there's still a lot of drag as it's trying to slow down. That's pushing it forward, so it's the opposite. So it's still going forward-ish direction. It's kind of hard to explain without being able to use my hands.
Well, I'll tell you this. I understand your reasoning. I will say you don't need to worry about drag and air resistance right now. Technically, you're right, but we're not worrying about that. I will say you got the right answer, but I'm going to give a better reason. Here's going to be my reason. You know when you slam on the brakes? What happens? When you slam on the brakes in the car, don't you want to go forward, but your seatbelt stops you? Why does the seatbelt stop you? Because the seatbelt is pushing in the opposite direction. For the same reason, these crate of apples wants to go forward. It wants to move forward. It wants to crash into the back of this wall. But it doesn't. Why not? Because of static friction pointing that way. And not only is it static friction, because if it was just static friction, what would my equation be? Trick question. There would be no equation because it's less than or equal to. But since it's asking for the minimum stopping distance, that means we need the max static friction force. And why does that matter? Because Fs max static friction force, is the only time you get to use the equal sign. And that's equal to mu s times the normal force. So I give us that the coefficient of static friction is 0.5, so that's 0.5 right there. I don't know the normal force yet, but I bet the normal force is equal to mg for the same reason we said earlier. By the way, is normal force always equal to mg? The answer is no. There's two instances where it does not equal it. One is if you're on a ramp, and two is if there's any other forces in the y direction. For instance, that last problem we did with the suitcase, see how there's another force in the y direction? That means normal force does not equal gravity when that happens. We don't know the normal force. You could calculate it using F net y, which you could do if you wanted. I don't care. Anyways, Fn equals mg. It's still a problem because I don't know the mass of the apples, but I have a feeling it's going to cancel out because that's usually what happens in physics when I don't know a variable. So anyways, back to the problem. I'm doing F net x, and this is for the apples. It's equal to all the forces to the right, which is none, so 0, minus the forces to the left, Fs max. And that equals my mass times acceleration. Remember, this time my acceleration is not 0. Why not? Because the acceleration, you're slowing down. If you're slowing down, the acceleration can't be 0. It's probably a negative number. So anyways, negative Fs max is going to be negative mu s times normal force. And if I actually plug in those variables, where mu s was 0.5 and normal force is mg, I can set that equal to ma. And again, it looks like my mass cancels because it shows up on both sides. So the acceleration is equal to negative 0.5 times g, which is 9.8. That's going to give me an acceleration of negative 4.9 meters per second squared. Now notice, this is not the final answer. What is it then? Well, what are we solving for? We want to find a distance, right? A stopping distance. And I gave us a velocity. I hope you realize this is a kinematics problem when it comes down to it. So what do we do for kinematics? Well, I'm going to write down the variables I know and what I want to solve for. Like, for instance, the initial speed is 16 meters per second. We just found the acceleration. It's negative 4.9 meters per second squared. I want to solve for delta x, which is the distance. That's what I'm solving for. Are there any other variables I know? Because right now I don't have enough. I need 3 to solve. The correct answer is I know v final. How? Because didn't I say we're coming to a stop? Yeah, so v final is 0. You gotta catch that to remember it. So now I'm going to use the equation that does not have time in it, and hopefully you remember this kinematic equation. It's v final squared equals v initial squared plus 2 times a times delta x. So v final is 0 equals v initial, which is 16 squared, plus 2 times negative 4.9 times delta x. And now I just got to start solving using the algebra. So for instance, 0 equals 16 squared is 256, minus 2 times 4.9 is 9.8, delta x. We're going to add 9.8 delta x to both sides, so 9.8 delta x equals 256. And then you just got to divide both sides by 9.8. So 256 divided by 9.8, it's going to be a final distance of 26.1 meters. That is the minimum stopping distance if you don't want the crate of apples to slide. And by the way, that's about a little bit less, just less than 30 yards, like probably 28 yards, I bet. Okay. With that, that's going to conclude today's very fun lesson. Are there any questions on anything we talked about today? Okay, if not, you are free to go. I'll be posting the homework soon. Thank you all for watching, and I hope you have a great rest of your Thursday night. Take care, and bye-bye.